Good afternoon, everyone, and thank you for joining us on this cloudy and wintry January afternoon. For those of you that I have not had the opportunity to meet, my name is Sandy Haas. I'm the Executive Director of the Retirement Association and serving as your host today. In addition to our distinguished speaker with me today is Program Coordinator Millard Sussman. It is my pleasure to introduce a member of the Electronic Technology Committee who is serving as today's lead program coordinator. Please join me in welcoming Millard Sussman for the purpose of an introduction of our distinguished speaker. Okay, Millard, it's all yours.
Thank you, Sandy. Well, Happy New Year, everyone. This is the beginning of the programs for the UW Retirement Association for the year 2022, and welcome to all of you. I have the honor of introducing today's speaker, Professor Mark Sassman. Professor Sassman has been a faculty member in the Department of Physics at the University of Wisconsin since 1999. He's currently director of the Wisconsin Quantum Institute, which is based in the Department of Physics and has connections with computer science, electrical and computer engineering, engineering physics, materials science and engineering, chemistry and statistics. Professor Sassman received his bachelor's education in applied physics at Caltech and his doctoral training in physics at the University of Colorado Boulder. I don't have time to list all his professional activities since he received his PhD, but I will note that he's the author of something on the order of 150 research publications and has been principal investigator on grants that add up to more than $35 million over the course of his career. He's received numerous professional awards, serves on the editorial board of the Physical Review, major publication in physics, and is a grant reviewer for the National Science Foundation and a number of other granting organizations. He lists his research interests as quantum information processing, atomic physics, laser cooling, quantum optics, nonlinear optics, and dynamics. We've all been hearing about the potential wonders of quantum computing and wondering what it's all about. Well, today we have the opportunity to get the answer to that question from the director of one of the nation's leading research programs in quantum computing. So it's with great pleasure that I introduce Professor Mark Sassman. Take it away, Mark.
Thank you, Millard, and good afternoon to the Retirement Association of University of Wisconsin-Madison. Happy New Year. It's really a pleasure to be here and to kick off this year's talks to the Retirement Association. Let me just share my screen here. Figure this out. And get that to full screen. And I think you should be seeing my screen now. So what I want to talk to you about today is quantum computing. And I've added the additional phrase climbing Mount Entanglement. And I'm sure many of you have heard at least something about quantum computing. And this is somewhat of a difficult topic to explain to non-experts exactly what it is. I think probably all, or at least almost all of us, have some sense of what computing is about. And indeed, almost everyone today has in their pocket or in front of them a cell phone, which is a very powerful computer, in fact. Nonetheless, there's some limits to what these computers based on electronics and silicon technology are capable of. And quantum computing is a new approach to computing that potentially will be very transformative and will lead to computational capabilities that we will never be able to access, even with continued progress in classical electronics. So what I thought I'd do today is sort of divide this webinar into three parts. I'm going to start out by talking a bit about quantum mechanics, because quantum computing has something to do with quantum mechanics. And so quantum mechanics is also kind of a difficult topic, but I'll try and distill part of the essence of quantum mechanics, which is important for having a sense of what quantum computing is all about. And then I'll try and show you a bit about how quantum computing works, what makes a quantum computer tick. And then, time permitting, I'll show you about some of the approaches that are being used today, and in particular, the approach that my research group focuses on to actually building quantum computing hardware and making it available. Let me also say that because this is indeed a complicated topic, I'm very happy to make this a conversation. So please, if you have questions or comments or points of clarification along the way, you really don't need to save them till the end, but feel free to put a question into the Q&A, and I think Millard will alert me, and we can address those as we go along. Okay, I'm in the physics department at UW-Madison. As Millard mentioned, I'm also working with the Wisconsin Quantum Institute that serves as a focal point for quantum science and engineering across the campus. And my research is supported by a number of government agencies. Let me just see if I can turn on my pointer here. Here we go. A number of agencies listed here. And for full disclosure, I want to also mention that I also spend part of my time working with a company called Quanta, which is working to commercialize quantum technologies, including quantum computing. And Cold Quanta is based in Colorado, but we also opened an office here in Madison, and my research group actually collaborates closely with Cold Quanta, and a number of graduates from my group and other groups are now employed at Cold Quanta working to develop quantum computers. So with that introduction, let me jump right into it and start by talking a little bit about classical and quantum mechanics, because the capabilities of a quantum computer rely on some aspects of quantum mechanics. And when we think about phenomena that we encounter at macroscopic scales in everyday life, they are very well described by classical physics. And when I say classical physics, I'm thinking of Newton's laws of motion, F equals ma, Maxwell's equations that describe electromagnetism. And these foundational pillars of classical physics work extremely well in many, but not all cases. When we dig down to the level of the very small, individual particles, individual atoms, the classical physics description of how the world works no longer applies. And we get into a realm where quantum mechanics takes over. And when we get into that quantum mechanical realm, some things change and are no longer easily understandable based on our everyday intuition. And so let me try and address one of the key differences between a classical mechanics and or classical physics and a quantum mechanics description of the world. And in a nutshell, one of the central elements of a quantum mechanical description of the physical world that we live in is that quantum mechanics gives up on certainty and describes the world with amplitudes and probabilities. Quantum mechanics is still a predictive theory, and indeed calculations based on quantum mechanics are remarkably accurate in predicting how the world works, but at the level of individual events, the way quantum mechanics describes the world is not in the form of a definite prediction, but really in the form of probabilities for different events to happen. And let me try and walk you through an example of that. So if we think about classical mechanics and maybe excuse me, simplest example of that, the motion of a classical particle, we describe that motion of a classical particle in terms of a path that depends on time. So if I call the position of this particle x and the time coordinate t, the particle's moving along some path and its position is a function of time x of t. Kind of thing we'd encounter in an introductory mechanics class. And classical mechanics is predictive, which is to say that if we have some initial conditions, that is, we know the position at some initial time t init, and we know the momentum, which is the mass times the velocity of the particle at that same initial time t init, then we can use Newton's laws of motion to calculate x at later times, and also the momentum or the mass times the velocity for any later time greater than t init. And the motion is deterministic. We specify an initial condition, we know Newton's laws of motion, and we're able to very accurately predict position and velocity at a later time. And that works extremely well. This is the basis, for example, for predicting the motion of satellites that we launch into space, and everything works out just fine. When we describe the motion of a particle in quantum mechanics, it is in principle not possible to know x of t and p of t simultaneously, and that inability to know both of those quantities with arbitrary precision at the same time is codified in Heisenberg's uncertainty principle, that the uncertainty in the position times the uncertainty in the momentum is never smaller than 1/2 of h bar, Planck's constant. And there's kind of a philosophical question here. Is this a matter of us not being smart enough to know what x and t and p of t are simultaneously? Or should we think of it as there is no simultaneous x of t and p of t, that particles actually don't follow a specific path, but have a more complicated and less definite trajectory through position and momentum phase space? And I don't want to get into questions of reality and what the right way of thinking about that is. I leave that to the listener to decide for themselves. But suffice it to say that within the theoretical framework of quantum mechanics, we give up on the notion of knowing x of t and p of t simultaneously and describe them using the Schrodinger equation or the Heisenberg equation in a non-deterministic, probabilistic fashion. And so that has some consequences. And perhaps the paradigmatic example of that is the two-slit experiment. And this is a very interesting experiment that has been done many, many times, and the results of which fully support the quantum mechanical description of nature. And this experiment is based on the following construction. We have a source on the left here. We have a screen that has two apertures or two slits that we'll label A and B. And on the other side of the screen, there's a detector where we measure the arrival of particles or waves at this location. And so here's a picture of that two-slit experiment from really a classic textbook in physics, the Feynman lectures on physics from about 60 years ago now. And as an undergraduate at Caltech, the course was not taught by Feynman, but we used some of these lectures on physics as part of that course. And so he gives a picture in his lectures of the two-slit experiment and says, let's first imagine this experiment with classical particles. So I have a source of particles on the left here. The particles emerge in a fan, and those particles can pass through slit number 1 or slit number 2. and then they're observed on this backstop here with a detector that can move up and down to observe the distribution of particles on the screen after the slits in the aperture. And if one of the slits were to be open, one would observe this distribution P1 that's sort of centered over the slit 1. And if slit 2 were open, one would observe the distribution P2 that's centered a little bit lower down because aperture 2 is lower down. And if we open both slits at the same time, we would just see the sum of those, which would have the particles most likely to arrive in the center and then falling off to either side. So that's the situation if we have two apertures and we send classical particles through one at a time, we would observe this distribution on the output. Really no surprises there. And you could certainly do this experiment by having a source of sand, say, and dropping the sand down through an aperture like this. And you'd observe a sort of pile of sand like this at the bottom. Now, if we do this experiment with quantum particles, and when I say quantum particles, I mean particles that move following the laws of quantum mechanics and interfere with each other, what do we observe? Well, again, if we just open one of the slits at a time, we'd observe a distribution P1 or P2 that looks essentially the same as the distribution seen with classical particles. However, in this case, if we open both slits at a time, what do we see? Well, we see something very different. We see interference. And that is, there's, again, a maximum probability of observing a particle right at the center, but it doesn't fall off monotonically to either side. There's interference, and such that if we parked our detector right here, we'd have a very small probability of ever observing a particle. One would also see this kind of pattern just from the interference of waves. If we had a source of waves here that could travel through both apertures and then interfere, one sees this kind of wave-like interference. And so that quantum pattern is clearly very different than this classical pattern where there's no interference. Okay, so how should we think about that classical interference occurring in a situation like this where we have an aperture with two slits? Well, the experiment has been done many times, and perhaps the first time it was done was quite a long time ago, even before the invention of quantum mechanics, by Geoffrey Taylor. And I'll tell you a little story about this. So Taylor was a very prominent, if not the most prominent, fluid mechanics scientist of the previous century, working in Cambridge. And I know a little bit about him because my father actually worked with G.I. Taylor over the years. And so I had the honor of meeting him a couple times. And although Taylor went on to be very prominent in fluid mechanics, he started his career as a young student at Cambridge, at Trinity College, also being interested in quantum phenomena. And he set up an experiment where he had a candle and he made the light emanate, actually not a candle, an oil lamp. He caused the light from the lamp to be very, very dim by putting some blackened plates after the lamp, and then allowed the light to pass through a screen and recorded the interference pattern on a photographic film. And he made the light so dim that it took about 3 months for the longest exposure of the film that he actually produced. And he made the light that dim such that one could estimate that at any given time, only one particle of light, one photon, was passing through the screen, causing a diffraction pattern. And the story is, why did he choose an experiment that took such a long time to perform? Well, I think presaging his career in fluid mechanics, Taylor was an avid sailor and he wanted to get out of the lab and go sailing. So he set up this experiment that would run by itself for 3 months and he could go off sailing and have a good time. So he set up this experiment that very slowly exposed a very weak light source passing through a diffraction pattern onto a screen. And he used a gas flame and a slit. And a simple calculation showed, just to give you a sense of how weak the light was, the amount of energy falling on the plate during the longest exposure was the same as that due to a standard candle burning at a distance slightly exceeding a mile. So he did this experiment, and what he observed was interference with light waves, but he observed that interference with such weak light waves that really just one particle of light was passing through the screen at one time, and nonetheless, he still observed an interference pattern. Now, this is not the actual data that Taylor obtained in 1909, but this is data from an equivalent experiment done by other people more recently. But this shows that even when one photon at a time passes through a two-slit structure like this, an interference pattern emerges. And so that's kind of mysterious. You know, how can one particle, in this case a photon, a particle of light, pass through two different slits at one time in order to interfere? And certainly if the particle just goes through one slit, we would not expect any interference pattern to occur. Now, light's a mysterious thing, and photons and particles of light are also mysterious. And so one might say, well, it's not really a particle, it's a wave. And so I don't care if the light was very feeble, I still expect to see wave interference, so that's not very surprising. But with advances in technology, people have now actually done this experiment with particles. And so people have observed, and this is some work from about a decade ago from a group in Vienna, Austria. They've observed quantum spatial superposition with molecules. And so they had a source of a molecular beam source that was collimated and also passed through a grating structure that had slits. And with a position-dependent detector, they were able to very clearly observe interference patterns from these molecules passing through these slits. And these were, you know, moderately large organic molecules with different structures, each of which contained many atoms. And this really starts to boggle the mind. How do these molecules go through two slits at once to form an interference pattern? And so this goes back to this quantum mechanical description of reality that gives up on the notion of a definite path. And the way we talk about it quantum mechanically is that there's an amplitude for each molecule to go through either one of the slits, and there's a phase associated with those trajectories, and those phases interfere and which causes interference. And so, you know, how exactly does that happen? Well, that's a quantum mystery. I can't give you an explanation, but this is what quantum mechanics predicts, and this is also what's observed. So at the quantum mechanical level, I hope you are getting the notion that the quantum mechanics is very strange, and at the microscopic level, the way the world works is certainly not intuitive and is strange. So that was kind of a long introduction. What's that got to do with quantum computing? This talk's supposed to be about quantum computing. Well, I hope I've given you the sense that particles can be in two places at once. They must have gone through both of those slits in order to create an interference pattern. And so it's not such a stretch to imagine that if a particle can be in two places at once, I can also use a particle to represent two data values at once. And that's part of the basis for the power of a quantum computer. And so what I'll go ahead and talk about now is tell you a bit about what qubits are, or quantum bits of information, and then how they fit into actually running a quantum computer. But maybe I'll just stop there and certainly ask if there's any questions at this point. Okay, I guess I'm not seeing it.
No questions yet, Mark.
Okay, that's fine. That's fine. So let me proceed and talk about qubits. So I'll get to qubits in 1 second, but first a little bit more introduction. You know, we've had this amazing growth in the development of calculational power over the last century and more. And I kind of like this chart, which shows calculations per second per constant dollar. So that's kind of a sort of interesting unit to think about it in. And, you know, 100 plus years ago, calculators were mechanical machines, starting with, the name slips my mind now, Babbage, who created the mechanical calculating engine in the 1800s. Then we had electromechanical relays, we had vacuum tubes, we had transistors, we had integrated circuits. And Gordon Moore's law describes the exponential growth of computing power. But the era that exponential growth is drawing towards a close. We're still experiencing increases in computing power. The rate of increase has slowed down somewhat. And as the latest transistor chips get to the level where individual transistors are now no more than a few atoms, we're getting into this regime where quantum mechanics plays a role. But quantum computers are more than that. They hold the promise of really a radically different way of doing computation and the promise of new exponential advances compared to classical machines. And government has been investing in this for many years, and it's been an accelerated investment over the last decade or so. I think the UK was the first government to have a very large-scale quantum technology program. The European Union has a program. China has been investing very heavily in quantum information, and in some areas is now leading the world in these fields. And in the US, we have a national quantum initiative for a couple of years now that's also investing substantial sums in quantum technologies. Beyond that, commercial interests have started to pay significant interest in this area. And that's both the largest companies in the world, the Googles, Microsofts, IBMs, and Intels, and others, but also a large range of startups, including the one I'm working with, called Quanta, who are competing to develop quantum computing capabilities. And the timeline for the ideas about quantum computing really started in the early 1980s. Richard Feynman most prominently put forth some of the first ideas about using quantum computers to solve problems in physics. And about a decade after that, we started to see specific numerical problems, a toy problem in the first instance introduced by David Deutsch, but then a very important problem introduced by Peter Shor, which showed how to use a quantum computer to factor numbers more rapidly. That was followed by ideas for error correction and other advances in quantum computing. And in parallel with that, as I've indicated with this colored font, we started to see physical implementations of systems suitable for quantum computing, starting with macroscopic coherence in superconductors, experiments with trapped ions, experiments with quantum dots in semiconductors, experiments with neutral atoms, and other approaches to creating entanglement. So the field as such, as a branch of physics and science, is about 40 years old, dating back to when quantum computers were proposed for tackling physics problems. And the field really took off in terms of government support for this research area, which was then followed a bit later by commercial interest, following the invention of algorithms that could really solve problems of interest. And I'll tell you a bit about this factoring problem and how Shor's algorithm changes the landscape. So we're now in the development stage of this new era of computing where there's a global race on to develop quantum computing capabilities that really stretches around the globe. And this graphic here is even a little bit out of date, but there's very substantial investments going on across the world. And yeah, the EU started a €1 billion program a few years back. And as I mentioned, we have a National Quantum Initiative program in the US. And a large part of that 1.3 billion investment has gone to establishing new quantum centers through some of the funding agencies. And here at UW-Madison, we have very significant participation in a couple of those centers, one managed by the National Science Foundation and one managed by the Department of Energy. And there's a publicly available overview document that can gives more insight into this national strategy that one can find on the web. And as I said, there's also companies involved. There's the giants of the world working on developing hardware and software for classical information problem. These companies all have now very significant investments in quantum computing. And there's also a whole range of startups, in fact, many more than I've indicated here. So what makes a quantum computer tick? Let me try and convey that without getting too deep into the technical minutiae. So the starting point is a quantum bit or a qubit. And if we think about a classical computer with digital representation of information, we're talking about classical bits of information. You can think of those as switches that can be either off or on, representing a 0 or a 1, so a binary representation of data. And if I have n classical bits, at any one time, I can store a single data value out of 2 to the n possibilities. So if I have 1 bit, n is 1, I can store 2 different data values, 0 or 1. If I have 2 bits, I can store 4 values, 0, 0, 0, 1, 1, 0, or 1, 1, and so on and so forth. So that's classical bits storing classical data. In the quantum world, we talk about qubits. And a qubit differs from a classical bit in that a qubit is not, we don't think of a qubit as being 0 or 1, but we think of a qubit as being 0 and 1. And here I'm using this quantum mechanical notation to represent the quantum 0 and the quantum 1 state. But we think of a qubit as being 0 and 1, or any combination of 0 and 1 with weightings given by coefficients a and b, any combination of 0 and 1 at one time. And the implication of that is that if we have n qubits, we can store 2 to the n different values, different data values, not one at a time, but simultaneously. And so if I had, for example, 2 qubits, I could represent 0, 0, 0, 1, 1, 0, and 1, 1 with some relative weighting all at one time. And the way exponential numbers work, if I had 100 qubits, and 100 is not that big a number, and we're now starting to see quantum computers with 100 qubits, 2 to the 100 is more than the number of particles in the universe by a huge factor, in fact. And so there's an enormous amount of data that could be stored in a machine that works with qubits, and that gives access to a kind of parallel processing that can speed up computations very significantly. And so that's the first difference, is that instead of working with classical bits, we're working with qubits. And that's taking advantage of quantum superposition. And again, think of that in the same sense that in the 2-slit experiment, this particle went through both slits at once, interfered, and created an interference pattern at the output. Here, the qubit is in two states at once. And if I have multiple qubits, those two states, each one in a superposition of states, they can all interfere and create, have superposition interfere, creating the output of the calculation. And so superposition is one aspect of the quantum world. The other aspect is entanglement. So this slide is probably the most math I'll have in any of the slides, but let me try and walk you through it. Let's imagine I have two qubits now. And qubit 1 is in a superposition of 0 and 1 with coefficients or amplitudes A0, A1. Qubit 2 is in a superposition with amplitudes B0 and B1. And if I put those two qubits together, just one multiplied by the other, I get a superposition of all four possible states. So as I just mentioned, with the two qubits, I can actually represent information corresponding to those four different states at one time, 0, 0, 0, 1, 1, 0, and 1, 1. And if I had n of those qubits, I could encode 2 to the n states at a single time. So that's superposition. And then there's entanglement. And entanglement involves preparing states of qubits that are not product states. They're not those two qubits multiplied together, but they're entangled states. So I could, if I have two qubits, let me go back here, and I multiply them together, I get some combination of those four basis states, the four possible combinations of 2 zeros and 2 ones. But I can also prepare states where I, for example, don't have any amplitude in these middle two, but I have something that looks like this, 0, 0, and 1, 1. And the interesting thing is that I cannot write that state as the product of the state of one qubit times the state of the other qubit. This is an entangled state. Let's think of those qubits as atoms, and I'll show you a bit later how we use qubits as atoms. And so atom 1 is in the superposition of state 0 and state 1. And atom 2 is in a superposition of state 0 and state 1. But they're in a entangled superposition, which has very strong correlations, and I can't describe the physical state of those two qubits as being separable from each other. And this entanglement is what Schrödinger thought of as an essential feature of quantum mechanics. He called it Verschrängung, which is translated into entanglement. And such an entangled state cannot be described in terms of classical bits. It's not a product state. There's no way of expressing this state as the state of qubit 1 times the state of qubit 2. And there's no way of locally and realistically describing these entangled states. Einstein and his co-workers saw this as a shortcoming of quantum mechanics, although it's since been decisively shown experimentally that such entanglement definitely exists. And when we think about quantum computers and the way in which they speed up computations compared to classical computers, part of it derives from superposition, part of it derives from entanglement. It's not completely clear exactly where the speed up comes from, but the power of quantum computers does appear to be intimately related to the presence of entanglement, for the simple reason that if there was no entanglement, we could use a classical description of the machine. But because there is entanglement inside a quantum computation, we no longer have a classical description. And so the quantum computer goes beyond what's possible classically. Interesting to know the person who showed how to experimentally resolve this Einstein-Podolsky-Rosen paradox was John Bell, and he wrote his seminal paper on this topic while visiting the physics department in Madison back in 1964. So actually, even before quantum computing became popular, there's been a really key connection between the University here in Madison and this quantum science topic.
Mark,
So-
I have a question for you.
Sure.
In the entanglement equation, there are no symbols for amplitude. In general, can there be?
There can be. So what I've drawn here is what turns out to be a maximally entangled state. So there's a threshold for entanglement. You can be below the threshold and not be entangled, or above the threshold and be entangled. And then you can get further and further above the threshold, depending on the relative amplitude of those two states, and get more and more entangled. And when the amplitude of the 0, 0 and the 1, 1 is the same, that's the state that has the most possible entanglement of two qubits. And we refer to this as a Bell state, actually, in honor of John Bell. But one can generalize that to have lesser amounts of entanglement than the maximum. So going on then to how to think about data processing on a quantum computer, first going back to the classical description, well, a classical central processing unit, or CPU, one has some input data, which would be a string of binary bits in a binary representation, and one sequentially passes those input data strings into the CPU. Each one of those input data strings generates an output data, and so we have sequential data processing. That's how classical computers operate. In the quantum world, we think about it in a different way. We have a number of qubits that we combine together to perform a large superposition. And if we have n qubits, we form a superposition of 2 to the n different quantum states, each with a certain amplitude, A, B, C, D, and so on. And we pass that superposition, and they're in general, to start with, there's no entanglement here. Entanglement will be created during the calculation, but we pass this product state of all the qubits into our quantum CPU, and what we get out is another transformed state of those n qubits, where all the coefficients, A, B, C, D, have now been transformed into A prime, B prime, C prime, and so on. And so we're doing a large amount of parallel processing in one go by putting all these different data values into the quantum CPU or QPU and getting our output data in one go. And so the results for all possible input data are computed in parallel, and that's great. On the other hand, the result is only determined probabilistically. So I didn't talk about this yet, but when we measure a quantum superposition state, what we observe is we never directly observe this entire wave function or entire superposition. We observe one of these 2 to the n states with probabilities A prime squared or B prime squared or C prime squared, and so on. And so although we computed all these possible input data in parallel, the result only gives us one particular output, and that result is in fact only probabilistic. We don't guarantee of getting a particular output. Quantum mechanics just tells us the relative likelihood or probability for observing a specific output. So that's a very strange computer. You know, if our laptop only gave us a certain answer probabilistically, we'd send it back to be fixed. That wouldn't be very satisfactory. So let's take another look at what I just said, how this quantum computer works. Let's say I prepare a handful of qubits here, and I prepare them all in the state 0 as an input, and I run that into my quantum computer. And that quantum computer is going to perform some operations on these qubits. They're going to interact with each other, and I'm going to get some more complicated states coming out. And so the output state, the quantum mechanical output state, is itself deterministic, And these arrows I have pointing in different directions, I want you to think of those as representing the output state of a particular qubit being, in this case, mostly along 0, with a little likelihood of pointing down, which would be state 1. The output qubit might be unchanged, still pointing up, which is state 0. And so if I look at that qubit, I'll always measure state 0. But if I look at these qubits like this one pointing to the side, half the time I'll observe state 0 and half the time I'll observe state 1. So every time I measure the output of this quantum computer, I'll get a string of 0s and 1s, but that string will be different every time I measure, except in the case where the qubit is pointing along a well-defined direction towards 0 or 1. And so the output string is probabilistic. And what's special about quantum algorithms or the circuits that we run on a quantum computer is that they somehow extract useful information from uncertain data. And again, that's quite different than the way that a typical classical computer operates. And an implication of that is that although quantum computers are potentially extremely powerful, they're not going to be good for everything. The quantum computer is not going to replace the computer in your pocket that deals with telephone messages and text messages and email. It's not going to replace a laptop for writing documents or surfing the web, but it is going to be useful for some different types of calculations that are difficult to perform on a quantum computer. And so this kind of picture of quantum computing has been codified into something we call the circuit model of quantum computing, where we have as an input n qubits, each of which is in a quantum superposition state. We feed those n qubits into our quantum processing unit that performs some operation on the qubits that transforms their state, and we get the n qubits out in transformed states, and then we make measurements on those qubits to determine the result of the calculation. And just as a classical computing machine has a finite set of logic gates that can be composed together to perform an arbitrary calculation, so too in the quantum world, any arbitrarily complicated U operation acting on all n of these qubits can be decomposed into operations that operate on a single qubit at a time. We would call that a 1-qubit gate, or 2 qubits at a time that we would call a 2-qubit gate. And the 1-qubit gates we can think of in terms of this block sphere picture of a qubit. So we represent a superposition state of a qubit, some combination of the state 0 and state 1. We can represent that as a position on the surface of a sphere, with the North Pole being state 0 and the South Pole being state 1, and any individual qubit can be represented by an arbitrary position on the surface of the sphere. And we manipulate and control those qubits by operating on them with rotation operators, X, Y, and Z operators that rotate the state of the qubit about X, Y, and Z on the sphere. So we have this very compact and useful geometrical representation of the state of 1 qubit in terms of a position on the surface of the sphere. Now, this works very well for a single qubit. It doesn't work that well when we have 2 qubits or more, because then we're in a higher dimensional space that is not so easy to visualize. But this is very useful representation for a single qubit. And for 2-qubit gates, these are essential for performing quantum calculations and essential for preparing entangled states, such as the Bell states that I mentioned. And the prototypical 2-qubit gate is the controlled NOT gate. And this is the quantum equivalent of, for those of you who are familiar with digital logic, the exclusive OR gate when we talk about digital binary logic. And the 2-qubit C0 gate takes 2 qubits as inputs. There's a control qubit C and a target qubit T. And the operation of this qubit, we can think of the sum of C plus T mod 2, or base 2. So the operation of this gate, said another way, is that if the control qubit is in state 0, then nothing happens. Both the control qubit and the target qubit are not changed. But if the control qubit is in state 1, then the target qubit gets flipped. So a 0 goes to a 1 goes to a 0. And that operation of flipping or nodding the target qubit is mathematically the same as addition mod 2, or the exclusive OR operation. So that's a C0 gate, and that gate combined with rotations on the Bloch sphere is all one needs to do an arbitrary quantum calculation acting on qubits. And so combining those two elements, we can create entanglement on demand. So here's a circuit that takes 2 qubits in a product state, both qubits in state 0. This H is a particular rotation through an angle of 90 degrees, one of those qubits. And then this is the C0 gate symbol. And that operation creates one of the Bell states with a relative amplitude actually of I. And let me walk you through that. So if I start here with 2 qubits, I can write that as the state 0, 0. This rotation here, H, creates a superposition of 0 and 1. It's a superposition with equal probability, but there's a particular phase, the imaginary I, multiplying the state 1. And if I expand that out, I'm in a 2-qubit superposition of 2 qubits in state 0 and the 2 in the states 1, 0. I then run that through the C0 gate, this thing here, 0, 0 goes to 0, 0, but the 1, 0, where 1 is the control qubit, that acts on the target to flip it, so that becomes 1, 1. And this is indeed, apart from this I coefficient, equivalent to that maximally entangled Bell state. So I prepared entanglement with this simple quantum circuit. And this is the kind of thing we do every day in the lab, working with our qubits and our quantum computer. So the first really significant quantum algorithm that really opened up for greatly expanding activity in the field of quantum computing was Peter Shor's invention or discovery of the quantum factoring algorithm. And if one has a number with n bits, we have classical algorithms for finding the factors of that number. And the best known classical algorithm takes a time to factor an n-bit number that scales according to this expression given here. So it's not quite exponential. It's kind of an odd looking expression. It's e to the log n times log squared of n to the 1/3 power. But this is an expression that grows faster than any polynomial expression, but is somewhat sub-exponential. And that exponential growth, or super polynomial growth more precisely, in the time it takes classically to factor an n-bit number, means that it's practically impossible to factor numbers with more than about 1,000 digits. And as I'll explain in a moment, that lies behind the security of, for example, purchasing things on the internet. Shor's quantum algorithm, if we have a quantum computer that can operate on n qubits, this will factor a large number in a time that goes as log n to the 3rd power. So exponentially faster than the classical algorithm. And the invention of this algorithm opened up the floodgates for huge activity in quantum computing. Why is that important? Well, there's something called RSA public key cryptography. This is something that was invented by Rivest, Shamir, and Edelman. This public key crypto system in 1977. Actually, that's not quite true. It was independently invented by Cox in England in 1973, but kept secret because it had security applications. And the way public key cryptography works is that if one wants to share a secret message between two parties over a public channel without an eavesdropper being able to intercept that message, one first shares a public key that's known to everyone and a private key. The messages are encrypted with the public key and broadcast, and only recipients who know the private key can decrypt the message. So this does require some secure way of sharing the private key between two parties. They might have to meet or send a letter to each other or something. But if that can be done, then this can be used to protect personal data on the internet, for example, online shopping. And the security of this RSA public key cryptography system that's very widely used to protect data relies on the difficulty of factoring large numbers. And so there's an organization that actually put out a public competition with monetary prizes for factoring larger and larger numbers. So this organization, RSA, established increasingly large numbers with increasing numbers of decimal digits. So the number here on the RSA label is the number of decimal digits in that number. And in 1994, they awarded a prize of $100 to these people who factored that number. Some years later, they gave $1,000 to people who factored a number with 174 decimal digits. They then gave $2,000 for factoring an even larger number. And then they stopped doing it because there were too many people factoring numbers. The largest number that it's publicly known to be factored is RSA 768. And these are the factors in green and red. And it's, of course, not difficult on a computer to multiply those two numbers and verify that the product of those numbers is RSA 768. But if I were just to give you RSA 768, it would be extremely difficult for you to find the factors. And in fact, this was done using the classical number field sieve algorithm that has this scaling with the time. And it took about 1,500 years of compute power on an AMD 64 to factor that number. And the way this expression scales, if you doubled the number of digits in that number to RSA 1536 with the same speed classical chips, it would take 200 billion years. So it would essentially be impossible to factor that number. Yet if you had a quantum computer, you could do it a whole lot faster. So just to drive this point home, here's a graph of the time to factor an n-bit number on a classical computer using this number field sieve algorithm. So the time in a logarithmic scale going from a second up to 1 billion years versus the number of bits. And so this is for 500 bits on 2003 era, 2003 era PCs. It would take about a month. If we had faster PCs, as in 2018, you could shorten the time a bit down to maybe an hour, but it's still growing exponentially. So if you increase the number of bits, it doesn't matter how fast the computers are, it's just going to take a time corresponding to the age of the universe. Now, these green lines here are the scaling of the time running Shor's algorithm, and it's just a very different scaling, such that even if you had a very large number and a not particularly fast clock rate on your quantum computer, you could factor an extremely large number in a substantial amount of time, but still tremendously faster, exponentially faster than you could on a classical computer. So this motivated a lot of people to try and build a machine that could actually do this. And let me say very clearly, we don't have such machines yet. We are making progress, but we're still a long way from being able to factor a number that you could not factor today on a classical machine. So Shor's algorithm is one of the grand challenges in this field, but let me give you one other example of a quantum algorithm that has a quantum speed up, but which is a lot easier perhaps to understand. Exactly how Shor's algorithm works is really a topic for when I teach my class on quantum computing. And even in that class, after a month of introduction to quantum computing, it takes a whole week to actually explain how the algorithm works. It's quite complicated. Here's an example of something simpler, which predated Shor's algorithm by a few years, called the Deutsch-Joshua algorithm. And it considers the following toy problem. Let's say I have a function f, which is a relatively simple function, which has a 1-bit input. And so that input has a value of 0 or 1, and maps it onto a 1-bit output, which is also 0 or 1. So this is a function that takes a 0 or 1 as an input and gives 0 or 1 as an output. And there's 4 possibilities for that function. That function could take both inputs, 0 and 1, and give 0 as output. It could give 0 for the 0 input and 1 for the 1 input. It could give 1 for the 0 input and 0 for the 1 input. Or it could give 1 as the output for both inputs, okay? So there's 4 possibilities for this function f that maps 1 bit in to 1 bit out. And we divide those 4 possibilities into 2 types. If the output bits is the same for both inputs, we call that a constant function. And if the output is different for the 2 possible inputs, we call that a balanced function, okay? So that's the truth table for the 4 possible functions f. And that function, 1 bit in, 1 to 1 bit out, can be either constant or balanced. And then we pose the question, I give you a function f, is it a constant function or a balanced function? And the function f internally might be very complicated. I mean, the way the function acts on data is quite simple, 1 bit in to 1 bit out, but the internal workings of the function could be some quite complicated algorithm. And so classically, if I want to figure out if it's a constant or a balanced function, the only way to know is to evaluate the function twice. I would evaluate the function with 0 as the input, and I would evaluate the function with 1 as the input. And depending on what I get out, I would know if it's constant or balanced. Remarkably, using a quantum circuit, we only need a single evaluation of the function f, and we can determine if it's a constant or a balanced function. Now, this is a toy problem. It doesn't have any applications that I'm aware of, but it highlights the distinction between classical and quantum computational capabilities. And again, it's a little bit hard to understand how that works. These 4 circuits I've drawn here correspond to the action of the 4 different possible functions f, but inputting qubits that are prepared in any of those 4 states into that function, into that circuit, can tell us if the circuit and therefore the function is constant or balanced with only a single evaluation of the function. So again, this is a little bit mysterious and it would take too long to go into more detail about exactly what's going on, but what comes out is what one gets in the second output bit by running these circuits is the addition of the input bit and the function evaluation on the other bit, mod 2, and that's enough to determine if it was a constant or a balanced function. So that's something that we can do quantum mechanically with one evaluation, but we cannot do classically. So I'm going to again just stop there for a second and take a sip of water here, and again be happy to take any questions, and then I will go on to give you some insight into how do you actually build these things physically.
I don't have any written questions, Mark.
Okay, I'll assume that means everything is crystal clear or entirely opaque, one of the two. Maybe we're in a quantum superposition of those two possibilities.
They're both correct, yes.
Okay. So how do we build these machines that work with qubits and create lots of entanglement and do calculations exponentially faster than we could classically? How do we get up this mount entanglement? And how far away is this? Well, there's a range of approaches to building quantum computers. And what I'm showing you on this slide here are the 5 primary approaches that are being investigated today. And these 5 primary approaches are being investigated in academia, at universities like UW-Madison and many, many other places, at government research labs, and also in industry. And you can kind of divide these approaches into a couple different classes. One class is atomic qubits, where we use either neutral atoms or we use atoms that are missing one electron, so they have a charge, so they're ions. And so we're using either arrays of trapped neutral atoms or arrays of trapped ions. And on the trapped ions, qubit machines with about 20 qubits have been demonstrated so far. On the neutral atom approach, people have put together arrays of 100 qubits. In fact, my research group, works with this neutral atom approach. We've even done arrays of more than 1,000 qubits, although we're not yet able to use all 1,000 in a quantum computer. So that's one atomic approach. And this is a nice approach because all the qubits are identical. They're individual atoms or ions, and they're essentially free. Another approach is based on engineered qubits, using either superconducting devices or semiconductor quantum dot devices. And these engineered qubits are not all identical, and that gives some additional complications when running a quantum computer in terms of keeping track of the differences between the individual qubits, although that can be done. The current sort of state of the art in actual working quantum computers is actually set by the superconducting hardware, by teams at Google, at IBM. And in fact, the most powerful chip for which data has been made publicly available so far is from a research group at the USTC University in China. So they're right at the forefront of this field. I'll also mention that IBM recently announced a superconducting chip with 127 qubits, although as far as I know, they haven't actually released any data yet on how well that chip is working. And the quantum dots are still at the level of a couple qubits, although working hard to scale up. And then there's another approach that uses particles of light, photons, as in that two-slit experiment to actually build a quantum computer. This is a very difficult approach in terms of scalability, I would claim. Some people disagree with me, and in particular people working on this approach, but photons don't directly interact with each other, which in many ways makes it difficult to scale this approach, but the time will tell. And just to mention, here at UW-Madison in the physics department, we have very active research activities in these three approaches: neutral atoms, quantum dots, and superconductors. So we really are one of the centers worldwide for qubit technologies. So, and this is shameless, but I'll mention a book that I recently co-authored that for those who want to dig even deeper, includes chapters in all 5 of these approaches and really gets into the physics of how these things work. Although this is not an easy read, it's for someone who has an actual physics background. So a quantum computer is only going to be more powerful when it gets to the size and quality at which it's surpassing what can be done on the classical computer. And so one might ask, well, how many qubits could I simulate on a classical machine? And remember, if I have n qubits, the number of states those n qubits represent scales as 2 to the power n. And so the amount of memory I would need in a classical computer that's simulating my quantum computer grows as 2 to the n. And these dots represent large-scale, brute force, classical simulations of quantum computers up to just shy of about 50 qubits. And although people introduce particular methods and have used modern computers with enormous amounts of memory, even going up to 1 petabyte, this is really going to run out of steam. In fact, the worldwide storage available to Google, last I looked, is something like 10 exabytes, which would correspond to about 60 qubits. So one is never going to be able to brute force simulate the operation of a quantum computer on a classical machine beyond about 60 qubits. So, and therefore, if we have a working quantum computer with more than 60 qubits, then we're in a regime where we can start to do things that you just cannot do classically. It is true that one can trade off this exponential requirement in memory by not trying to simulate or calculate the full quantum state output, but just calculate the probability of observing different outcomes, which is all we have access to in an experiment anyway. And one can do that by trading off memory for time in a way that allows one to simulate more qubits. So it's possible to simulate the probability of different outcomes corresponding to experiments with more than 60 qubits, but only for a circuit that has a limited depth. If one wants to simulate many qubits for very deep circuits corresponding to long calculations, then the number of possible paths that the quantum superposition follows in that circuit gets exponentially large, so it takes exponential time. So one can trade off memory for time, but the time grows exponentially. So again, last I looked, the state of the art was something like 140 qubits, but only at a circuit depth about 30 deep. And that would not, there's also classical ways, and that would not give you a beyond classical calculational performance. So we've not yet decisively passed the classical limits for problems of real world interest, but we're starting to get close to that with quantum machines. And so one of the approaches people are looking at, given today's hardware that has a limited number of quantum bits and also is limited in the accuracy and fidelity of those quantum gate operations that can be performed, and therefore limited in the complexity of the quantum circuits that can be run, people are looking for ways of nonetheless extracting an advantage from these noisy, imperfect machines. And this is being referred to by John Preskill as the NISQ era. You know, in classical world, we have RISC processors, a certain chip architecture for faster computation. In the quantum world, we're living in this disk era for noisy intermediate scale quantum. And a lot of activity these days is focused on actually on hybrid approaches, where one has a classical optimization loop that's coupled with a quantum coprocessor, where the job of the quantum machine, the quantum processor, is to prepare a quantum state of n qubits that's then measured, and that would be exponentially hard, either in terms of memory or in terms of time on a classical machine. But then the circuit that's preparing that quantum state is determined by a classical optimizer in a way that drives the quantum state that comes out of the coprocessor to a particular quantum state that solves a computational problem. And so there's algorithms for doing this, hybrid classical quantum algorithms referred to as variational quantum eigensolvers and quantum approximate optimization algorithms. And these are some of the algorithms that are really generating a lot of attention and work these days. And they can be used for things like quantum machine learning and quantum artificial intelligence. So just to go in a little bit more detail on that, the way this works is there's a quantum device that prepares a particular quantum state that's then measured. The measurement output is fed back into a classical optimization calculation that feeds back, that determines a set of parameters that feed into which gates we include in our quantum circuit, that changes the quantum state we get out. And so one loops around this multiple times in a way that solves a computational problem. And so this is being used for solving problems in physics. It's being used for machine learning tasks on hybrid quantum computers. This is a reference to a paper from people at the Rigetti Computing Company. This is a startup working with superconducting quantum computers. And this can be used for things like unsupervised learning. And unsupervised learning is something that can be mapped onto a graph problem, a combinatorial optimization problem that's called maxcut. And the maxcut problem seeks to divide a graph into two sets of vertices such that the number of connections between vertices in different sets is maximized. So here's a picture of that for a small graph. Supposing I have a graph with 5 nodes, and those nodes are connected according to the lines that are drawn here. And I want to divide those nodes into either white nodes or black nodes in a way that the lines connecting nodes connect nodes in opposite classes. And so that seems like a kind of abstract graph problem, and I suppose it is. But it turns out this is a problem that cannot be efficiently solved on a classical computer. It's in the complexity class NP hard, and that means there's no deterministic polynomial time algorithm that can actually solve this problem. There's efficient approximate solvers, but there's no efficient classical algorithm that will guarantee the best solution to this problem. And it turns out there's a lot of real world use cases for solving this problem. Unsupervised learning, resource allocation in wireless networks, traveling salesman type problems. There's actually many cases that can be mapped onto this type of problem. And this problem can be solved with the QA-OA algorithm on hardware, and has been solved in small instances on real hardware. And I'll give you an example of that. This is from some data, very recent data from my own lab, where we solved QA-OA for a very simple graph here, 3 nodes on a line. And the maxcut solution to that problem is that the center node is in a different class than the outer two nodes. So either here I've used blue and red, either the center one's blue and the outer two are red, and vice versa. And again, I won't explain it, but here's the quantum circuit that we ran to implement the QAOA algorithm on these 3 qubits. And so we prepared 3 qubits on the left. We ran through a sequence of gate operations, and these 2 black circles with a line are part of controlled NOT operations that we ran on those qubits. And what came out of it was a distribution. What came out of it was a quantum state that we then ran this many times and measured the quantum state and generated a probability distribution. And what we saw is that mostly we got out the state labeled as 010 or 101, corresponding to the center node being in the opposite state. So blue and red are here represented as zeros and ones. And clearly we see a strong probability to be in one of the max cut solutions. And there's lots of gory details in this preprint here. So that's an example of running a quantum circuit. And this was done with neutral atom hardware. Here's another example with a slightly more complicated graph, a 4-node graph, again, where the central node is connected to the other 3. And the max cut solution is where that central node is an opposite color of the other 3. And one runs this algorithm multiple times in a sequence, giving longer and longer circuits. And here's once through. So that's this upper row here with a not too long a circuit. If we run twice through, which is a twice longer circuit, we get better probabilities of ending up in the correct states. That's represented by this number here. And then if we run 3 times through, theoretically it should get better, but because our hardware is noisy, it actually got a little worse again. And that is just showing we ran into the limitation of our current hardware. So that's again an example of an algorithm for solving a graph problem. And this current state of the art in this is some work done by Google on a superconducting chip where they solved this kind of problem on a graph with about 20 nodes. And their hardware, they had more qubits and they had less noise. And so they were able to do this on a larger circuit with more nodes, but still not beyond what one could do classically. So, there's a lot of activity going on to build these things. And let me take the remaining time to dig in a little bit deeper to some of the actual experimental work going on here at UW-Madison. And our work is supported by multiple federal agencies I've indicated here. We have our Quantum Institute to bring together the research across campus on this. WRF also supports this, and we're also part of the Chicago Quantum Exchange, which is based down in Chicago, and which includes us and other Midwest-based universities and partners. And there's also a number of companies that different research groups here are collaborating with as part of these efforts, and even American Family Insurance, which is not a quantum computing company, has generously supported us because of their interest in data processing. And they have a data science group who are looking to the future and want to stay abreast of developments in quantum computing. So, as I mentioned, this early work understanding how to determine experimentally aspects of this Einstein-Podolsky-Rosen paradox was done by John Bell when he was in Madison. That was a long time ago. The work on campus started about 20 years ago. Some of us in the physics department, some of us in computer sciences, Dieter's in computer sciences, and we've had our different interests. And this has blossomed into a large number of faculty. In fact, even this slide's a little bit out of date. We're now more than 30 faculty distributed across a couple colleges and many departments on campus, working on different aspects, and not just quantum computing, but using qubits also for making better sensors, better measurement devices, and also for doing secure computation, secure communication. I mentioned that public key cryptography is at risk of quantum computers that can factor large numbers. On the other hand, one can use quantum systems to transmit data securely without being subject to factoring machines, allowing eavesdropping to occur. I'm not talking about that today, but that's another application of these quantum technologies. And we're faculty across the campus are working on qubits and quantum computing, working on quantum networking, quantum sensing and metrology, looking towards applications, and we're also involved in workforce development. And in the physics department, we've established a professional master's program in the physics of quantum computing, which is training people, many of whom go on to industry jobs in this sector. So focusing in on the qubit research, there's 3 platforms being very actively developed here. Silicon quantum dots, which is an effort led by Mark Erickson and collaborators. Superconducting circuits, which is led by Robert McDermott and collaborators. And I work with a number of faculty to develop neutral atom arrays for quantum computing. And since neutral atoms are what I'm closest to and I know the most about, I thought I'd take a few minutes and try and give you a flavor of, well, how do these things actually work? You know, what is involved in building a quantum computer using neutral atoms? So here's a picture of one of my labs, and it's pretty complicated. You know, there's a lot of stuff in there. There's a lot of electronics, a lot of lasers, signal generators, optics, complicated things. Way back here, this is the quantum processing unit where there's a vacuum cell holding atoms, where we actually have our qubits, and a lot of this equipment out here feeds into that quantum processing unit through electrical cables and through optical fibers carrying laser light that controls the qubits and actually performs the quantum calculations. So here's more of a close-up of the central part of the computer. And again, you can't see the vacuum chamber with the atoms. It's hidden behind here, but you can see there's a lot of complicated looking optics and devices for steering laser beams around that interact with individual atoms, control their quantum state, and perform their the quantum circuit calculations. So these are, you know, these are not computers that you can put in your pocket yet. Nonetheless, you know, companies are producing better engineered versions of these things, and the Cold Quanta company I work with expects to have a version of this type of computer available later this year that will be available through a cloud access to people who want to use it and run quantum circuits on it. So the qubits that we work with in the atomic approach to quantum computing, each qubit is an individual atom. And to perform a full quantum computation, there's a set of requirements. We have to be able to initialize our qubits into a particular quantum state. Say we'd like to start with all the qubits in state 0, start the computation. We need to have good coherence, and what that means is that we can prepare a superposition of state 0 and 1, say put the qubit in this position on the Bloch sphere, and have that superposition be maintained without decohering, without interacting with the environment and decaying. And that's a key parameter of quantum computers. And with atomic qubits, we are able to demonstrate coherence times of many seconds. So that's actually good. We need to be able to measure the quantum state after the calculation to extract the results. And we can do that by scattering light from the qubits, basically taking pictures of them in a state-dependent way. We need to perform a set of logical gates, rotations of the qubit, these XYZ rotations and C0 gates. And if this is going to be useful, we need to be able to scale it up to create large arrays of qubits. And we think that we can solve all of these challenges using neutral atoms. If we look at the periodic table, there's of course many different atomic elements. The ones I've colored in are ones that have been used for laser cooling experiments. And there's different uses for these atoms, basic physics, atomic clocks, quantum computers, other types of sensors. In terms of quantum computing, attention has mainly focused on the alkali atoms, the heavy alkali atoms, rubidium and cesium, and also on alkaline earth atoms, strontium, and also rare earth atoms such as ytterbium. My group mainly works with rubidium and cesium. We also have some activity with holmium atoms. The qubit that we use when we work with cesium atoms, I like to think of as an industry standard qubit. Why do I say that? Well, if one looks at the ground state of cesium, cesium has a core of electrons and a single unpaired valence electron in this outermost shell. That's the electronic shell structure of cesium. And the interaction of that outermost valence electron with the nucleus splits the energy of that outermost electron into two levels that we call hyperfine levels. And the energy separation of those two states is the basis for the international definition of the second, the SI definition of the second. In physics, we measure energies in terms of frequencies. That is, an energy is Planck's constant times a frequency. And the amount of time corresponding to that number of oscillations, 9,192,631,770 oscillations of radiation, microwave radiation, that's resonant with that transition, that elapsed time is the definition of 1 second. So in many ways, cesium is an industry standard atom. And in my group, we use the same states of cesium, this state and this state, that define the second to define our qubit. And so that's the best characterized pair of atomic states that we have. And so we use that for our qubit. And we have techniques for preparing the cesium atom in a particular state, say this state, and then manipulating the atoms to create superpositions of those states and to prepare entanglement between multiple cesium atoms. And so the steps in actually running a quantum computer are, first, we shine laser light at atoms using techniques that I won't go into here in the interest of time, but remarkably, we can shine laser beams at atoms and cool them down from room temperature down to a few millionths of a degree above absolute zero. And we can do that very rapidly in a fraction of a second using, in fact, very relatively inexpensive low power lasers. And this works extremely well. And this is a picture of about 1 million laser cooled atoms at a few millionths of a degree above absolute zero. We then prepare an array of trapping sites using what you could think of as optical tweezers, a pattern of light that traps individual atoms in locations arranged on a grid. And when we do that, and that's using a different wavelength of laser light, when we do that, we get single atoms in some of the locations. Some places we get more than one atom, and some places we get no atoms. And then we take a picture. This is a camera picture. We take a picture of where the atoms are, and then we use yet another laser at a different wavelength to pick up the atoms and move them around and arrange them in a regular pattern that fills the array. So we have a very regular grid of atoms available that we can use as qubits in the computer. And so these three sequences, cooling, loading into the array, and then rearranging to fill the array, you can think of as controlling the mechanics, the quantum mechanics, if you like, but controlling the mechanics of the atoms. And then to do the computation, we have to control the quantum state. And that involves initializing these atoms into a particular state of the cesium atom, running a sequence of gate operations, and then measuring the results, determining if the atoms are in state 0 or state 1. And so I'll show you in a little bit more detail, without going all the way into the weeds, how we give you a flavor of how we do some of these things. So how do we create these patterns of light that trap the atoms? Well, we've done it in different ways over the years, starting with a single atom, and we've progressively scaled up to more and more atoms, such that our most recent results are actually trapping more than 1,000 atoms. And one of the ways we do this is using light that actually has a certain wavelength that repels the atoms. And by forming cages with the repulsive light, so we create an array, a grid of lines of light, and we trap atoms in these little cages in between the lines, we can actually trap the atoms essentially in the dark, surrounded by walls of light that keep them in place. And that's very good because the atoms are essentially in the dark, they're not perturbed by the trapping light, and they have very good coherence. And we can do that in a dynamical a way using these lines, and using some optical devices, we can change the number of lines and change the number of trapping sites. And very recently, we've done this with more than 1,000 sites using a little bit different method, method that we patented with WARF, but we've trapped now more than 1,200 cesium atoms in a grid. This is a picture of the pattern of light, which is a pattern of holes on a background of light that traps the atoms. And this is a picture of the actual scattered light from the atoms, showing that we're trapping them. This rearrangement is really quite fascinating. It can be done in 1D, 2D, and 3D. It was invented by groups in Korea, Paris, and at Harvard a few years ago, and is now being very widely used. And the most remarkable demonstration of this, I think, is this demonstration by the group in Paris of Antoine Brouet's, where they created a little Eiffel Tower out of individual atoms. So each one of these little dots you see here is a single rubidium atom, and they were able to arrange the atoms in 3D to create a small Eiffel Tower. Really quite fascinating. In my group, we're working in 2 dimensions, not 3. And so here, for example, we've spelled out physics, where each bright dot here is a single cesium atom on a grid with spacing of 3 microns. To measure the quantum states of these atoms, we do it basically by taking a picture of the atoms, by shining light at them, and then collecting that light on a camera. And the way this works is that we have available something called a cycling transition, in that we shine light which connects qubit state 1 with this excited state here. And after exciting that state, the atom will fall back into state 1 while emitting a photon. And we can cycle up and down from 1 to the excited state many times without falling into state 0. And so if we get a bright flash of light corresponding to this peak over here, we know the atom is in state 1. And if we don't get any light, we just get some background noise counts from the camera, we know we're in state 0. So just by taking a picture of the atoms in what is in principle a very simple approach, we can very accurately distinguish between quantum states 0 and 1. So we can perform measurements. And then to actually control the qubits, this starts getting complicated. This is the level diagram of cesium. The qubit lives down here in the ground state. And then we have microwaves connecting those two ground states, and then a whole bunch of different laser colors that connect the ground state with different excited states that are involved in making the atoms cold, in preparing a desired quantum state by what's called optical pumping, in measuring the quantum state, and in performing 1 qubit and 2 qubit gate operations on the qubits. And that involves just a lot of laser technology. We have, I think, 13 or 14 different laser systems to actually run the computer. And that's one of the engineering challenges, to get all that lasers and optics working well at the same time. But here's an example of rotating a qubit. We prepare the qubit in state 0, and this is this industry standard cesium qubit, where the energy separation of those two levels is 9.2 gigahertz. So we have a signal generator that generates 9.2 gigahertz microwave signal. We amplify it, and then we run it through a horn, and we illuminate an array of trapped atoms, and then we measure what state they're in, and those atoms rotate back and forth between state 0 and state 1, and that corresponds to rotating around that Bloch sphere in the Bloch sphere picture. And we can do this pretty fast. We did this originally at about a 10 kilohertz rate. We recently put in a bigger amplifier. We're now at about 75 kilohertz. And we can do this very precisely with a fidelity that's measured with 2 to 3 or 4 nines of fidelity. So rotations work really nicely. We can also rotate just a single atom at a time and not all of the atoms. And we need to do that for quantum circuit operations. And we can do that using a combination of microwaves and then a focused laser beam that just illuminates a single site and rotates one of those qubits without rotating the other ones. And so this is now happening much faster. This is on a microsecond time scale. We can do that with multiple at a time. Here's another example of that, where you can see that this qubit, which was in a bright state, was addressed with a focused laser beam and went into a dark state without perturbing the surrounding qubits. So putting this kind of control together, we can perform quantum circuits, and to create entanglement, we need to have these atoms to talk to each other. And what's very nice about these arrays of neutral atoms is that they really don't talk to each other. When they're sitting in these ground states, this industry standard qubit, even when they're very close to each other, just a few micron separation, they interact extremely weakly. That is to say, we'd have to wait 1,000 seconds before they had a noticeable interaction with each other. And so this is a very good quantum memory for storing quantum states for a long time. But to create entanglement and to run a circuit, we do need them to talk to each other. And to do that, what we do is we shine laser beams at the qubits to put them into very highly excited states that have very large wave functions. And those excited states interact very strongly. And again, I can't go into the details here, but those strongly interacting states, we know how to use that interaction to prepare entanglement and thereby implement a controlled NOT gate to complete our quantum circuits. And what's really neat about this atomic approach is we can go from this weakly interacting memory state to this strongly interacting logical gate state, where the change in the interaction strength is really enormous, 12 orders of magnitude. So we do that using laser pulses. This kind of shows you in a bit more detail what's going on. There's a small vacuum cell where we have the atoms trapped. We have some fast lenses looking in at the cell from a couple sides. We can image the atom array onto a very sensitive camera that can make these quantum state measurements. And then we can focus laser beams down to individual sites to perform quantum gates and to move the atoms around. And we do that using acousto-optic devices that can very rapidly scan the laser beams to different sites on microsecond timescales. And so we have 3 sets of these laser beam scanners to move the different laser beams around. So here's an example of creating an entangled state. There's a sequence of pulses up to these highly excited Rydberg states that create this 0, 0 plus 1, 1 state, where close to half the probability is in state 0, close to half is in state 1, and that we really have a coherent quantum state we see from this interference pattern shown here. And this is now creating a quantum state with a fidelity better than 95%. We need to keep improving this, pushing this up beyond 99%, but this is a recent good quality result that we've done here in Madison. And then we've used this for quantum circuits. I showed you some examples of this quantum approximate optimization algorithm. Here's another circuit we ran recently that actually solves a small quantum chemistry problem. This circuit, although it's impossible to know from looking at the circuit, this circuit is solving a problem of calculating the energy, the molecular energy of a hydrogen molecule by running a sequence of quantum gates. And we actually get that energy out to a few percent accuracy. And it's represented by a high probability being in this particular output state of this circuit here. So with that, I'm going to conclude and just say that quantum computing is a revolutionary approach to information processing. There's great potential for solving hitherto intractable problems. Although the hardware is very complicated, it's also primitive from the perspective of actually solving those problems, but it is under very rapid development. And it's hard to predict the future with any reliability, but given the number of smart people working on this, and also the large amount of resources going in to this field, both in the public domain, but also in the commercial domain, I think it's quite plausible that we're going to see some real useful advances in the next handful of years here. And so thank you for listening. I'll be happy to take any questions.
Well, thank you, Mark. That was dazzling. I do have a couple of questions that have piled up, so let me give you one of them. One of them says, with quantum computing, is it the case that we know all the possibilities, not just which answer of the possible answers?
Yeah, so great question. So let me go back one slide here, which I think maybe illuminates that question. So this is the encoding of a quantum chemistry problem related to the hydrogen molecule. And the way we ran this, we used 4 qubits. You can see the 4 qubits here. One of those qubits encoded this Hamiltonian. So one of the qubits encoded the physics of the hydrogen molecule. And the other 3 qubits are representing the energy, with not a very good resolution because we only had 3 qubits. So with those 3 qubits, we can represent 8 possible energies. And so to really do a super accurate calculation, we'd want more qubits. But with these 3 qubits, we can represent 8 possible energies. And what we find is that with highest probability, the energy lies in the range spanned by this particular state of those 3 qubits. Now, we also see, some non-zero results falling in these other states representing different energies. Most of that is due to the noise in our hardware. It's not a perfect quantum computer. And some of that is due to the noise in the algorithm. So quantum mechanics gives you probable outcomes, and it points to all the possible outcomes, but you may have to do some more work to actually convince yourself that the outcome you're seeing most probably is the answer to the problem that's being posed.
And there is a question back to properties going through slits. I guess that means particles. If the property is light, it would obviously go through more than one slit. So I think I'm missing the problem regarding interference.
Yeah, again, great question. So yes and no. So if we think about light in our everyday experience, it's a wave. It's a continuous quantity. The light can be brighter or dimmer. It's continuous. That wave of light would go through both slits, and we obviously have interference. But if we make the light very dim, as for example, G.I. Taylor did by having an oil lamp and putting some darkened plates in front of the lamp, and so he had a very dim light field. When we measure that very dim light with a very sensitive detector, we don't see waves, we see particles of light that we call photons. And we get individual clicks on our sensitive detector corresponding to individual photons. And it's those, because the light was very dim, only one photon at a time went through the slits. And so I want to say that one photon must have gone through one of the slits. And if you don't like that explanation that light is really particles, sort of both particles and waves, depending what regime you're in, if you don't like that, well, it was done with molecules, and those are definitely particles. But they exhibit wave-like interference because of quantum mechanics.
Mhm. The next question is, what are the energy requirements for quantum computing compared to classical?
It's also a very interesting question. So in principle, quantum computing is reversible. The operations we perform on the quantum circuit involve Hamiltonians and unitary operations. And in principle, it's reversible. And in principle, reversible computing can be done at no energy cost. So that's in principle. In practice, quantum computing requires a lot of energy. So we have in the lab right now, with our neutral atoms, we've been running circuits up to about 6 qubits. And with the same machine, I think we'll be able to run circuits up to maybe 20 or 30, maybe even 50 qubits relatively soon. The energy usage of that machine is about 20 kilowatts. So that's not very good. That said, there's actually one of the advantages that are foreseen for quantum computing is not just that we can calculate faster, but actually calculate more efficiently. I mean, modern supercomputers and quantum cloud installations where lots of data is stored use an enormous amount of energy. And so potentially quantum computing will be more energy efficient than classical computing, but we're not there yet.
And there's a question that begins with profuse thanks for a fascinating introduction and for giving your time so generously to the Retirement Association. The local connections from J.S. Bell to your lab, to Cold Quanta, and to the Quantum Institute were great. Are there many students at UW interested in studying quantum computing? Is interest growing? And do students interested in quantum computing come from some disciplines more than others? Math, chemistry, statistics, physics, engineering?
Sure. So the interest is definitely growing, and there's lots of students interested. This quantum computing activity here in Madison and also at other universities really started in physics departments. I mean, the field was started by physicists, and they had the early ideas about what it could be good for and how to build these things. But today it's much, much broader than that. And to really build practical quantum computers, that's not being done by physicists alone. It's really a collaborative effort between physics, engineering, computer science, math, statistics, and so on. And so it's much broader than that. I'd say the largest concentration here at the UW is in physics still, but there's a lot of faculty in electrical engineering, in chemistry, in computer sciences who are now also working on these topics. And we have lots of collaborations across campus between different departments and schools. And we offer courses in quantum computing and physics, and there's also courses being offered now in computer science, and I think there's emerging courses also in engineering physics also in terms of quantum sensors. Jen Choi is developing a course on that. And I have to say, I have more student interest than I can accommodate. I get every semester more undergraduates wanting to work on these topics in my lab than I can accommodate, and we have to turn people away. So it's very much a growing activity academically, and it's also a growing activity in the industry. And that industry, currently the biggest limiting factor in terms of this commercial development is workforce. There are not enough trained people in the quantum area to work on these problems in industry. And so as fast as we can train people, they get multiple job offers for very interesting and well-paid industry jobs to go work on these things. So it's really a very active field.
Well, that's all the questions. So it's remains only to thank you very much for giving us a deep look into what's going on at the University of Wisconsin and elsewhere. That was really quite an interesting journey through quantum computing. I don't think any of us are going to go home and try to put one together in our basement, but that was a dazzling performance. So thank you very much. We appreciate your giving us your time and letting us take a look into your world.
Well, thank you. Let me just say I enjoyed doing so. I'm very happy to do so. And if anyone has any follow-up questions, just feel free to shoot me an email. You can find me easily enough.
Great. Thank you.